So welcome all to week 11 tutorial for the course Deep Learning conducted by IIT Ropar. I'm Pintu Kumar. I'm a PhD scholar at IIT Bombay. So the topics that I plan to cover today includes the sequential methods, RNN, and towards the end we'll also look at LSTM and GRU. Okay, so this is plan for today. At any point during the lecture, if you have any kind of doubt or anything, you can either unmute yourself or you can type it in the chat box. I am sort of monitoring them. I'll try to answer. Okay, so let's begin. Okay, so first of all, let's try to look at what is the motivation for looking at these kind of methods. Okay, so the methods that we have looked so far includes our normal neural networks. Then we looked at some word embedding methods, right? We have also looked at autoencoders, and we have looked at things like CNNs, right? So these are the sort of methods that we have covered so far. So why do we need new methods? Okay, so whatever algorithms that we have covered so far, if you except for the word embedding in some sense, even the word embedding the techniques that we learned for word embeddings, if you look at these techniques, the input that you have in these word embedding techniques or neural network or autoencoders or CNNs, the input size is always fixed, right? For example, if you looked at some CNN, then your input size, you had to convert every image to a particular size to be able to process that. Okay, so the input size in some sense is always fixed. Okay, and the second drawback of these kind of methods is that like whatever input we give, let's say we have x1, x2, x3, these are our data points. Okay, so if we give x1 as an input, we can give any like the second input that we give x2, these two inputs are independent of each other. Okay, so that data set that you have, the data points that you have are independent of each other, right? But this need not be necessarily true. Okay, let's look at an example. Okay, so let's say you want to process a sentence through a neural network. Okay, let's say what you want to do is given some movie review that you have, you want to predict whether the sentiment of that review is positive or negative. Okay, or what you want to do is, let's say you have some Twitter posts. Okay, so you want to predict in real time whether that post is hateful or not. So you don't want a lot of hateful content on your social network sites. So you want a method to predict whether the content that is there is hateful or not. Okay, so these kind of applications are very much important. Okay, so what are the methods available with us to deal with these methods? We are going to cover those today. So now if you look at some sentence, the sentence need not have fixed number of words. Okay, for example, this sentence has 4 words, the second one has 5 words. Okay, so you can't keep on creating different networks for different length of sentences. You need a uniform network that can process all these varying sequence lengths, and so that's where RNN comes into picture. Another thing is, like, in a sequence of words, that is your sentence, the relative positioning of your words makes a lot of difference. For example, if you look at this example, pay up my dues. Here, dues is used as a noun, right? And if you look over here, I came in due time. So due over here acts as an adjective. Okay. So based on what are the words around it, based on the words that appeared before it, or you can say that what is the nature of this word. Okay, so let's say you have a task where you have to predict a figure of speech of a particular word, then not only that word becomes important, but the words that you have encountered before or after that also becomes important. Okay, so this is another, this is related to the second point that I mentioned, that each input need not be independent of the previous input that you had. Okay, so we want algorithm that can take care of both these things, that can has varying shape of input. By that I mean that can has varying length of input. And the second point is that we want to capture some form of dependency between the occurring words. Okay, so these kind of tasks are known as sequential tasks, and some of the example in like where it is applied is in NLP. NLP is your natural language processing. So all these sentences and these kind of things, in these kind of tasks, your sequential methods become important. Another like application where it is important is speech, like anything related to speech, because speech comes in form of a sequence and you want to process that sequence. Okay. Also, you can see videos as sequence of images. Okay. So this is another place where you have application to these kind of methods. Okay. Okay. So let's look at our first algorithm, that is RNN. Okay. So RNN is also called as recurrent neural network. So RNN is abbreviation for recurrent neural network. So your network would look only like this. So the portion I'm highlighting in the yellow, right? Your network would look only like this. This repeated like thing that I have shown is sort of a representation of how the like data is processed. But in reality, your RNN would look only this much. Okay. So what are the components of your RNN? So you will have an input. Let's say this is your input. X1 is your, let's say, first word, or it is an input. You have a matrix by which it gets multiplied. So it is very similar to your normal neural network. You have some input, right? And then this weight matrix is represented by U, and you have some intermediate layer, right? So this intermediate layer over here is represented by S. Okay, let's say this is S1, right? Right now you just consider it as S1. So if you give X1 as your input, you obtain your intermediate layer as S1. Okay, but the number of neurons and everything is same over here. So this much is only the neural network. So you right now forget about the rest of the part. So what you can do is you can simply forget about whatever is over here. So networks looks something only this much. Okay. So you have X1 as an input, you have some intermediate layer, then again you pass it on to your some output layer. Let's say there are two output neurons, and this is your Y. Y is a vector, let's say belonging to R2, which is your output. This is very similar to your neural network that you have been doing since, let's say, week 2 or 3. Okay. So what is different in like an RNN or a normal neural network? So what is different is, so let's say you passed your first input X1 and you obtain the output for that, that is your Y1. What you will do is, you will save your intermediate representation, that is you will save the S1. Okay, so after inputting X1, the intermediate representation that you obtained, you will save that S1, and when you are inputting your next input, let's say when you are inputting your X2, what you will do is, you will multiply this S1 by some W, and you will include that in the hidden representation of your next input. Okay, so let's see how does that work. Okay, so what is happening over here is, so one thing that you should remember, and that is an important point, the underlying architecture remains same. Okay, so the underlying architecture, the weights that you have for U, W, V, everything remains same, only your inputs vary. Okay, so what is the special trick that you do in RNN is, like this is your input, you pass it on, you obtain something known as S1. Okay, now when you are inputting X2, you obtain let's say this is intermediate, so let's say this is I2. Okay, so in order to obtain S2, what you do is, in I2 you add W times S1. Okay, and then you pass it on to your output layer. Similarly, and you name this thing as S2. This is your S2 now. I2 plus W times S1. Now when you again go for X3, you again multiply this thing by W, and you pass the output that you obtain from here, right? and this way you obtain your S3. Okay, so this is how your RNN works. So your SI is nothing but mu of xi, that is your input being passed till this point, plus w times of previous intermediate representation that you have and some bias, and then you have applied some non-linearity on top of it. Okay, now over here your u, w and b are your learnable parameters, similar to your neural network, right? These are your learnable parameters. Okay, also how does your loss function look? So if you recall, let's say this is a classification task. Okay, right now we are considering only classification task, where you had to classify it as one of your figure of speeches, whether it is a noun, pronoun, adjective, and those kind of things. So recall, if you had a normal neural network, for a particular xi, you would have cross entropy loss, right? Cross entropy calculated at xi comma yi, right? And if you had n such data points, how does your loss looks? It is sum of cross entropies, right? And similar thing happens over here also. So let's say in a sentence you have n words, so it is sum from 1 to n cross entropy at all the words, right? And if you simplify this cross entropy, it looks like log of ytc, where ytc is your predicted probability, right? So this is very simple, you can derive. This would be something like pi log of ytk. So for other values of pi you have 0, and only at cth position you have 1. So this becomes minus log ytc, and the value you obtain is minus of log ytc. Okay. So your loss function for your RNN is nothing but sum of cross entropies. Okay. So the loss function is sum of cross entropy. Okay. Okay, so any doubt in RNN architecture that we have discussed so far? Like, if you have any doubt in how, like, what is different in RNN architecture, or any point is not clear in whatever we discussed till now?
Sir, in case of RNN,
Yes.
whether xn can be greater than Sn, is it possible? Or both has to be equal?
What do you mean by greater than? So you are asking whether xn can
The
be?
dimension of xn is greater than dimension of Sn.
So in general, what will happen is that the dimension of xn will be greater than dimension of Sn. So if you look at a normal neural network, so your input, you generally try to reduce its size, right? So this is your input. There is a possibility that, yeah, there is a possibility that your size of xn, so the dimension of xn is greater than a dimension of Sn, and there is also a possibility that dimension of Sn is greater than equal to dimension of x. This is very much possible.
So we have to calculate the learnable parameters according to Sn, isn't it, sir? It doesn't depend upon Xn.
No, it will depend on xn. Let me clarify on that one. Okay, let's say
Yes, sir.
this is your dimension d. Xn belongs to your dimension d. So this is d size vector. Okay, and this is your some n size vector. Let's say this is some k size vector, because n is over here already. Let's say this is some k size vector. So we don't want to check whether k is greater than equal to d, or d is greater than equal to k. We are not interested in that. If you just want to check the number of learnable parameters or the learnable parameters. So the learnable parameter over here is u for u. Okay. So the only thing that you need to learn is u over here. So you need u to be such a matrix that, let's say this is u times xn is your Sn, right? So you need to find the dimension of u then. Okay, so this is your d cross 1, this is n cross 1. So what should be the dimension of u? Dimension of u should be n cross d. So based on dimension of u, you can have like whatever dimension you. So you have n cross d learnable parameters over here. Was I clear?
Okay, sir.
Okay. Okay, so there are, did somebody write something? No, okay. So there are 3 questions. Now this is an RNN architecture. Okay. So again, you have some input, you have some hidden layer, and you have some output. And like if you look at one of these blocks, right? If you just look at one of these blocks, if you just look at this much portion, this is given over here, right? This thing is given over here. So one of the block is drawn over here explicitly. Okay. So your input dimension is 2, right? And it is being mapped to a hidden dimension of 3. So again, similar to what you asked, let's say if this is my U, then U would be some 3 cross 2, right? And again, your output is given to be Y. So what was the matrix that they were using for output? Output was V. So your V would be now 2 cross 3. Okay, so something simple. Okay, so the question that is asked over here is, so this is your one of these layers. Okay, so this is the architecture of RNN that you have, and you will use the same architecture, but you will sort of keep passing different inputs along with the states from the previous input. Okay, so now the question over here is, how many neurons are there in the hidden layer at S2? So it is asking, let's say this is my X2, now this is my S2. How many neurons are there in the hidden layer of S2? Can you guys answer how many neurons are there in hidden layer of S2?
3, sir.
Yeah, 3 is correct. So because as I mentioned few moments ago, all these networks are same, their weights, their biases, the architecture, everything is same. Just the input changes and accordingly the like this SI changes. Okay, SI minus 1 changes. So because it is shown that the hidden layer has 3 inputs for your first input, let's say. So for second one also you will have 3 neurons only in the hidden layer. Okay. Okay. So on the same figure we have second question. So you have this question. Can you please answer this for me? It would be better if you can type so that others can also type. So we have trained the above RNN and it has learned weight and biases accordingly. Okay. If the weight of X1 to H11, okay. So what it is saying is, like they have trained this network and the weight that it has learned from X1 to H11 is 2. So for S5, when they were training for this S5 thing, they learned that the weight is 2. Okay. What will be the weight value of the same weight at S6? So when they are inputting the 6th word, let's say, what would be the weight? This is what their question is. So, okay, I'll come to the question. So can you please tell me what would be the weight be? So when they were learning at S5, their weight they came out as 2. Yeah, 2 is correct answer, right? Because as I mentioned, the architecture remains same, so the weight won't change till the time they have not updated the weight. Okay, like if at S6 now they have updated the weight, then it might change, but right now it won't change. Okay. Okay, so this is the third question. What is the dimension of matrix W? Can you please answer this question? Let's say this is A, B, C, D. Okay, so I'll again come back to this figure. So in RNN, W is the matrix over here, which gets multiplied by your previous states, and that is added to your input that you are giving. so that you obtain your SIs. Okay, so this is the exact formulation for your, so you can look at the W over here. So this is the matrix W, and we are interested in weight of the size of this particular matrix. Okay, so can you guys please tell me what would be the size of this matrix? Okay, somebody says 2 cross 2. Let's see what others says, then we can solve this question. Okay, so in this multiplication, if you see, what does W gets multiplied with? So this formulations look something like, this is U times X of I think I'm correct, yeah, W times Si minus 1 plus B, right? So W gets multiplied by Si minus 1. Now this Si minus 1 is, let's say, D cross 1. Let's say this is D cross 1, okay? Then my W should be also some X cross D, so that the multiplication is well defined. I don't know what my X is right now. Let's say this, that's why I'm representing it by X. But the number of columns that you should have is D, right? So that the multiplication agree. Okay, so right now what I can infer is that my matrix is some X cross D. Okay, now I'm adding it to something. So all these three terms, this particular term, this particular term, and this particular term should have same dimension, right? And what should be that dimension? That should be the dimension of Si. Now what is dimension of Si? Si is D cross 1. Okay, so what is the product that I obtain from here? The dimension of product is X cross 1, and that should be equal to D cross 1. Okay, so the dimension of my matrix W should be D cross D, right? What is D? Where D is my dimension of my hidden state, Si or Si minus 1, and those kinds of things. Now if you look at this example, what is the dimension of hidden state? Dimension of hidden state is 3. There are 3 neurons in the hidden state, right? So what should be the dimension of parametric matrix W? Dimension should be R3 cross 3. Okay, I hope this example was clear. Okay, okay, so I have a question for you guys, which was not from the assignment. Okay, so what I said is, like, when we motivate this RNN, the main motivation for RNN was that we want to tackle data sets which have varying shapes and sizes. Okay, so varying size eventually. So for example, I want to pass this statement also, that read only good books, or we are booked for Delhi. So this has 4 words in it. This has 5 words in it. Okay, so what I said is, like, no matter what is the size of your sentence, you can pass the first word, then you can pass the second word and use the intermediate representation that you got from first word to merge it in the representation of the second word, so that you can obtain the output. And you can repeat this process for the number of words that you have in the sentence. Okay, but if you look at this particular example also, your input dimension was fixed. So like the xi that you are inputting, like for the first word, for the second word, for the third word, that thing is fixed. The only thing that is not fixed is the number of words that you have in a sentence. Okay, but now my question to you guys is, so if you look at this sentence, the words in this sentence are also of varying length. Okay, so this has only 2 like alphabets, this has 3, this has more alphabets. But now the algorithm that was given to us, the RNN, it has a fixed input for a word. So it has fixed input for words. So if you have varying length of words, and you have to perform some task at sentence level, so that you want to find the mood of a comment or the mood of a review. So now again the problem remains same, right? So the words have varying length, but you have a fixed input size. How do you tackle this? So this is my question to you. Like, we wanted to motivate this RNN in a way that it should not depend on the size of the input, okay, but it has a fixed input length, at least when you are inputting words to it. So how do you tackle varying length of words? I hope my question is clear. So you guys can think and type it in the chat box. So what I'm saying is, like, you had a varying length of sentences. Okay, right now I'm just interested in the input. I'm not even talking about the output. Okay, so why did you sort of created this? I'll try to repeat my question. I think I was not very clear with my question. Okay, so what I'm saying is, let's say you have a word, I go to school. This is a simple sentence, right? So if you look at this particular RNN, what will happen is, first of all, you will input I to this RNN. You will obtain some hidden representation S1. Then you will input S2, right? Then for X2, you will input go. So you will have some S2 and you will have some W times this hidden representation over here, so that you can obtain the output. Again, you will pass 2 to your third input, school to your fourth, and so on. So if you have a varying length of words in a sentence, that can be taken care like this. But if you now look at the architecture of one of these single portion, it has a fixed length input. Okay, so I can only pass input with size 2. So I cannot pass I cannot pass go. So I can pass go and 2, but I cannot pass school in it. Okay, so how do we tackle these kind of things? How do we tackle this problem? Because you will encounter words with varying size, right? How do you tackle this now? Yeah, encoding is correct answer. So what you will do is, you will use word encodings. Okay, so the week that we did on word embeddings, right? Word to vec and those kind of things are not waste. Okay, so what you will do is, so many people have sort of compiled large corpus of data, and they have come up with very good embeddings for these commonly used words. So what you will do is, you will use those common embeddings for your words, and you will pass those words over here. Okay. One another thing that is coming to my mind is, so when these people would have evaluated this or calculated this word embedding, they would have done it for some particular dimension. Let's say they have evaluated it for like they have converted every word to dimension 16. Okay, but you want to use something like you want your input layer to have only 8 dimension. So then you can do some kind of dimensionality reduction like PCA, or you can train a small autoencoder before passing it to your RNN. Those kind of things you can do. Okay. So here you will not pass the words as it is, rather you will pass the encoding of your words. Okay, this was the point that I wanted to do.
Sir, how can we calculate the dimension, sir?
A dimension of what?
Dimension of the word, particular word. You have mentioned 8, 16 or 8
Okay,
dimension, doesn't it?
so when you were doing word embedding, right? What you were doing is, you were converting every word to some vector in Rn, right? So this n is your dimension of your embedding. So you are converting it to vector. So length of your vector is the dimension of your embedding. That is what we mean by embedding when we talk in terms of, sorry, that is what we mean by dimension when we talk about embeddings. So the length of vector in which your word is encoded, that length is known as dimension. Okay. 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 So now I'm gonna go over a topic of vanishing or exploding gradient in RNN, but I'm not gonna do it in very much detail. Okay. So I'm gonna go very quickly over it just to solve the question in the assignment. Okay. So I'll just tell you some facts, and I'll sort of expect that you just trust in me, or you have watched the videos, and it would be definitely clear to you that this thing is true. Okay. So how does a loss function of an RNN look, that we have already covered. Okay, so this would be sum of your log ytc. Okay, now let's say for the fourth word your loss is L4 and you want to find its gradient. Okay, this is the task that you have at hand. Okay, so using the chain rule, it can be written as del of L4 by del of S4 multiplied by del of S4 by del of del W, right? This is simple chain rule that you have done in many different contexts in this course. Okay, now the second part over here, this S4, like if you go through the lecture, you will see that it can be calculated as this term. Okay, so this is summation from k is equal to 1 to 4. So this term you can write something like this. So this will be del S4 by del S1 into del S1. This is explicit. So what this plus means is when you are calculating your partial derivative, you treat your S1 as your constant term. Okay, divided by del W plus del S4 by del S2 into del S2 by del W and so on. So you will have these kind of summations. Okay, and now if you just look at this particular term, okay, only del S4 by del Sk terms of this form, this can further be expanded as product of these kind of terms. So what it is, this is like if you have del S4 by del S1, it would be something like del S4 by del S3 into del S3 by del S2 into del S2 by del S1, right? Then you will obtain your del S4 by del S1. So this is simply writing this thing as a product. Okay. Now again I'm skipping a lot of detail, and what I'm saying is that like if you bound this quantity, one of them, so this is del Sj by del Sj minus 1. So this is j and just previous to it, j minus 1. So the terms that would appear in product over here. So for example, S3 by S2, these kind of terms are bounded by norm of W. W is your matrix that you had, W matrix that we have been talking about in RN. Okay, multiplied by this norm of this diagonal matrix, sigma dash of Aj. Okay. Now the thing that I want to say is this sigma is your sigmoid activation function and any other activation function that you want to choose. For sigmoid activation function, the second norm is less than equal to 1 by 4. Okay, the second norm that you have is less than equal to 1 by 4. Okay, so what I'm trying to say is your, let me choose another color so that you know where I'm writing. So this del Sj by del Sj minus 1 for sigmoid activation is less than equal to norm of W times 1 by 4. Okay, now this was just for this del Sj by plus 1 by del Sj, right? This is del Sj by del Sj minus 1. Now if you want to bound the norm of, let's say, some del St by del Sk, so this T and K are not related in a manner in which your J and J minus 1 were related. So this thing is less than equal to norm of W times 1 by 4 to the power T minus K. Okay, because these are K terms multiplied with similar bounds, so if the product will have bound raised to the power T minus K. Okay, I think that is clear. So this is the norm that you have on, sort of the bound that you have on the norm of this thing, and these quantities will be added, multiplied and then added and those kind of things. Okay, so what I'm trying to say is the product that you have over here. So for example, for sigmoid activation, if this norm of W into 1 by 4, this thing is strictly less than 1, let's say this is less than 1, and this is raised to some power, let's say t minus k, where t and k have large gap between them. Okay, because this quantity is less than 1, the gradient that you will obtain would be close to 0. And in such cases, you will encounter vanishing gradient problem. Okay. Again, there is another case when your this term is strictly greater than 1. Okay. Then you will encounter exploding gradient problem. Okay. Uh, there have been few suggestions to counter exploding gradient problem. One suggestion is that whatever gradient you obtain, because that, let's say you wanted your gradient to be sort of in a particular range, and let's say your gradient has become quite large, then what you do is you divide your gradient by its norm. Then the norm of gradient is 1. Okay. Then you can in some way tackle your exploding gradient problem. But there is no similar solution for vanishing gradient problem. Okay. So you have a question in last year's assignment. I think there is a question in this year's assignment also. So what you are given is, in an RNN, norm of W is 3.5. So I think in this year's assignment you are given some eigenvalue, largest eigenvalue for W. So like you just search what is the relation between largest eigenvalue and the norm of this particular thing. If you are not able to find anything, just treat whatever eigenvalue you are given as the norm of your matrix W and then solve the question. Okay, in this year's assignment. So what we are given is that the norm is 3.5. The activation function used in RNN is logistic, or your sigmoid activation function. What can we say about del S20 by del S1? So this was the norm that we had on del ST by del SK. So what was the bound for it? It was norm of W into, this is the diagonal of this norm of diagonal this thing, right? So what we can say about this thing is, this is less than equal to norm of W is 3.5 times, now as I said, for sigmoid activation function, this lambda value is 1 by 4, right, into 1 by 4, this raised to the power t minus k. So this was st del st by del sk. So here t is 20, k is 1 to the power 19. Okay. So if you look carefully, the value inside is strictly less than 1. So even if it is, let's say 0.9 or something, if you raise it to the power 19, the value that you will obtain would be very close to 0. Okay. So the answer over here is the value of gradient is close to 0. S1 is a constant. No, S1 is not a constant. S1 is the representation, the intermediate layer that you obtain. So this was your neural network, right? This was your input. Let's say this is X. This H1, H2, H3 combined, you can write it as S. This is your S. This is S1, this is H2, and so on. So S1 is not a constant. S1 is the intermediate layer of your neural network, right? So we are sort of using vector over here. Okay. 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 So like we have covered RNN, let's discuss about some of the drawbacks that RNN has. Okay. Okay. So if we look at this architecture that we have, let's sort of erase this thing, whatever we have scribbled over here. Okay. So if you recall, what was happening is, let's say this is your 3 length vector, your S is 3 length vector. Okay. So you had S1 to begin with. In S2, what all did you store? First of all, you stored the input that was coming from your X2, and you stored all the previous information that was coming before S2. Okay. Similarly, at let's say Sn, what you are storing is, you are storing the input that you are having over here, as well as all the information that you are having from the previous steps. Okay. So in this process, what happens is you are sort of morphing information on one on the top of other on the top of other. So the information from initial layer sometimes might get some important information might get lost. Okay. So one drawback is because of the sort of limited size of your intermediate representation, you are morphing your information at each time step. So yeah, this is one drawback of RNN. Okay. So it is simply just like adding information. So this is one drawback. Second drawback we just discussed is exploding and vanishing gradient problem that we see in RNNs. Okay. So as an like impact of my first point that I made, because we are morphing information on each other, and because there is a vanishing gradient problem. So let's say if you see some error on step n, you can't actually very well estimate like what is the error at step n because of the S1, let's say. Okay. So because of the S1 representation that you get, what is the error at step n? Because the gradient with respect to the parameters of like this S1 parameters would be very small, and you won't be able to see what is the like how the error at these steps are related to the previous time step. So this is another drawback of RNN. Okay. So we have some more questions from previous year which are related to RNN. Okay, so select the task for which using an RNN will work better than other types of network. So over here, when I say other types of network, so you just consider architectures like normal neural networks, CNN, or autoencoders, right? Right now, don't consider algorithms like LSTM or GRUs. Okay, please don't consider these algorithms right now. You just compare it with these kind of algorithms, neural network, CNN, or autoencoders. Okay. So our RNN works, somebody says BD, let's say. Okay. So let's see what is the correct answer. So RNN would work better on all those kind of tasks where you have sequential data. Okay. Because these algorithms don't work great on sequential data. Okay. Now this image detection task, CNN does well on this task. So this option is not correct for us because there is no sequence involved in an image. Okay. First task is video captioning. As I mentioned in the beginning, and you would have seen a Patanjali video being played in the lecture also. So in video captioning, there are sequence of images that you see one after the other. Okay. So this is a sequential task. So RNN would perform better than these existing algorithms. Okay. Just the difference would be that the way you process data over here and the way you would have processed data in terms of video captioning would be different. So here what you did is you converted your normal neural network to sort of RNN by, so if these were your 3 hidden layers, you just kept on feeding this information back from the previous input. In case of image captioning, what you would have done is this normal neural network would have been replaced by a CNN, where your intermediate information would have been, you would have kept feeding the intermediate information to itself. Okay. So it would be a variant of RNN. Okay. Another thing is language translation. This is also correct because this is also sequential data. Okay. Last one is sentiment classification that we have been talking about from like the first minute of this class. So this is also true. Okay. So the second question is again what we have just discussed. Which of these neural network is best suited for sequential data? The answer is recurrent neural network. CNN are for images. Fully connected neural network, it can have varied applications, right? This is not just specific to something. Deep belief network is for generating data. We have not done this, but yeah, this is for generating data. So RNN is the correct answer over. Okay. Okay, so this is 6:50 right now. We can sort of take a 5 minutes break and we can meet back at 6:55. Then we'll discuss something about LSTMs. Till the time, if you have any
Can you show the drawbacks of RNN in the meanwhile?
Okay, yeah.
Thank you.
Okay, so we can continue with LSTM. Okay, so this is the example that was already mentioned in the class, but I want to motivate from the same example. Okay, so when we discussed about the drawbacks of RNN, the first drawback was because we have limited size of these SIs, okay, and we want to sort of write a lot of information in it. So the important information might get lost like in the meanwhile. So what we can do is we can use a smart way of select write, select read and select remove or erase to in order to sort of do a more efficient update of SIs. Okay. So right now what we are doing is we are just doing some u times of what is the input right now plus w times of st minus 1. Whatever was available till this point, you are capturing it in st minus 1. Sorry, si minus 1 because I'm using I over here. Sorry, plus some bias. Okay, so this is what we are doing in RNN right now. Okay, we want to modify this update of SIs in such a way that we are slightly smarter than what we are doing right now. Okay, so let's begin with an example. Let's say you have a board, okay, where you have only 3 lines available with you. So you can write only 3 statements. Okay, and you have to compute AC, right, BD plus whatever this expression is, you have to compute this. Okay, so let's say you went to like a, you were writing a maths exam, and this sort of question is given to you. How would you start writing? You would start writing by A is equal to 1, B is equal to 3, C is equal to 5, and D is equal to 11. But you are given only 3 statements that you can write, right? So even in just writing the things that are given to you, you will end up utilizing all your space. Similar thing might be possible over here also. Okay. So if you not selectively write the important things, you might end up utilizing your space for writing unnecessary things. For example, you might end up writing information related to your a, and, the, and these kind of things. Okay. So how can we smartly write this thing is, we can write these expressions. We can write AC, right? We can calculate it in mind. We can write AC is equal to 5, right? We can again write BD, right? BD is say 33. Okay. Now, second point is select read. Okay. So what select write means, like from the previous step, if you sort of think it in terms of RNN, so select write would mean, like from previous step, what are the information that you want to write in your S of t plus 1. So let's say you have information till S of t. What do you out of this S of t want to write in S of t plus 1? This is what would mean when you talk about select write. Okay. So what does select read means? Select read means from the amount of information that you have written out already. Okay. So the amount of information that you have written out already, what is the information that you want to use? This is what we mean by select read. So we have already written BD. Okay. So we want to use this information to calculate BD plus A, right? So BD plus A would mean 34, right? So in terms of RNN, again, when you talk about select read, when we will go to LSTM, and you have definitely watched the lectures, so there was a term called HT minus 1 or HT over here, right? So you have HT available with you, as well as you have XT plus 1 available with you. So out of these two information, what information you want to use in order to calculate ST plus 1, that would come under select read. Okay, similar to this, like whatever you have written till this point, what is the information that you want to use? Now to like involve extra information, like now the AC is of not right now, not this BD is of no use to me right now, right? So I want to include this, let's say AC into BD plus A I want to write. So what is the information that you are willing to remove from things that you have already written? That would come under select remove. So what is the information that you have already written? That is ST. So you want to remove something from ST, that is your previous step, this ST. And what is the amount of information that you want to remove from it? That would come in select remove. Okay. So let's look at all these things one by one. Okay. So one very small thing, let's say this is your vector S. Okay, this looks like something, let's say 1, 2, 3, 4. So when I say that we want to select some important information, one possibility is like let's say you say that first coordinate is important, third coordinate is important, I'll preserve these two coordinates, and everything else would be 0. Okay. Another option can be like you sort of weight these coordinates on basis of their importance. Okay. So what I'm saying is, let's say you multiply it with something like 0 0.9, 0 0.1, 0 0.9, 0 0.1. Okay. Now rather than, now what this LSTM or GRUs do is, rather than we giving them this explicit weights that they should multiply each element with, so this would be point-wise multiplication. This is not vector multiplication, but point-wise multiplication. Okay. So rather than we giving them the explicit weight, they will just multiply it with some weights. That would depend on some parameters that we'll come to. Let's say W2, W3, W4. Okay. So this is how they sort of extract the sort of important information that you want to read or write or remove. Okay. So what they would do is they would do a point-wise multiplication with a vector whose values are between 0 to 1, right? So because the values are between 0 to 1, and we have allowed these vectors to learn their weights. So we are implicitly allowing even weights like something like 1 0 1 0 that we saw in the beginning, right? So choosing the first coordinate and the third coordinate only. So we are giving it a richer space of vectors that it can choose from. Okay. Okay. So the first step is select right. Okay. So as I mentioned, what would come into select right is what is the information from the previous step that you want to write. Okay. So what is the information that is available to my till my previous step is s of t minus 1, right? So I want to do this kind of operation. Okay. I want to do this kind of operation on my s of t minus 1, right? So I want to multiply s of t minus 1 pointwise with some vectors whose value is between 0 to 1. Okay. How do I define such a vector? Now such a vector, that vector is represented by O of t minus 1. Okay. This is also known as output gate. Okay. This is given by sigmoid of something. Okay. Sigmoid of something. So why sigmoid? Because I want my value between 0 to 1. Okay. Now it is sigmoid of what? It is sigmoid of h of t minus 1. So this should be h of t minus 2. I'm sorry. Okay. So this is the selective right that you chose at the previous time step, h of t minus 2 multiplied by some matrix W plus U is a matrix multiplied by the input at that particular layer, xt minus 1 plus b naught. Okay. So this is what my output gate is, and this is how my selective right sort of works. I have to learn this W naught, U naught, and my bias B. These are the parameters that need to be learned. Okay. So after I learned my parameter, I'll know the weights of these this vector OT minus 1. Okay. That will be pointwise multiplied to give me h of t minus 1. And this process is known as selective right. So I'm extracting sort of the important information from the previous state st minus 1. Okay. Now what was the next step? Selective write. Sorry, selective read. What happened in selective read was whatever information is available with us, right? Whatever thing is available with us, what do we want to do to it? Okay. So selective write was like what information you want to write from the previous, like sort of all information that is given to you. So for that we applied operation of s of t minus 1. Okay. Now when we are doing selective read, we want to apply information on whatever we have written, right? So what have we written till now? We have written h of t minus 1. Okay. And at this particular step, we have also information about x of t. Okay. So we want to do read operation on both these things. Okay. So how can we sort of combine these two things? Again, like whenever you have to combine, you can do something like this. So this is w of ht minus 1 plus u times of xt. These are the two information that we wanted to combine with some bias again. Okay. So some bias b. Okay. Now this w, this u and b are similar to your the weights that you had in RNN or the normal weights of your LSTM. Okay. So these are not the special weights that you need to learn right now. These are your regular weights for RNN or LSTM. Okay. Here you had to learn special weights for OT minus 1. That was your gate. Okay. Okay. Now we have sort of created a modified vector s dash t that depends on ht minus 1, xt, and some bias. Okay. Why do we do this? Because the information that was available to us was ht minus 1 and xt, and we wanted to do a read operation on top of it. So we have obtained s dash t, which is a combined form of both these information. Okay. Now when we have combined form of both these operation, this is s tilde t. Now we want to do a read operation on this. So we want to extract important information out of it. So we again do a pointwise multiplication with a vector I of t right? So this is called input gate, right? So this is also similar to what we have defined for output gate. So this is wi h of t minus y. Now here we had h of t minus 2. Now here we have only h of t minus 1. ui x of t. In over there we had x of t minus 1. Here we have x of t and some bias. Okay. So all the gates that we will do will be of this form only. Some w times w star times h star plus u star times x star plus b. Okay. So this is the gate we have defined for now selective read. Okay. And we have obtained some output by doing point-wise dot product. Okay. So till now what we have done is we had some previous state. So this was the information that was available to us like from the previous time step. Okay. We created an output gate and did a selective write. So selective write would mean what information we want to write on our whiteboard. So this is the information that we wrote, right? Now, what does selective read do? Selective read is out of the information that is written with you, right? What is the information that you want to read out of it? Okay. So what all information was written with me? ht minus 1 was written and xt was written. So we partly mixed them to form a temporary state s tilde, right? That depends on ht minus 1 and xt, and we do a input gate on this. So we combined them together and then we extracted the important information out of it. So this is the thing that we have done. Okay. Now there is this last step that we did while calculation. So out of whatever was available with us, okay, now what is the information that we want to remove? Okay. So now to remove the information, we define something known as forget gate, okay, or the erase gate. So this is also very similar to what we have. This was also sigmoid wf ht minus 1 plus uf plus xt plus some bias. Okay. So we have these parameters u b naught, then we had wi ui bi. Now we have wf uf and bf. Now what quantity do we want to forget? Okay, so what was happening in case of RNN, what you were doing is, so you had some input, you have some s, this output, let's leave, this is input, this is some output. Okay, so you are mixing the SIs from here to the input over here. Okay, so we have like whatever thing we had written till now, we have extracted the important information from that. Now we want to add it to the sort of previous step that we had. Okay, so do we need all the information from previous step, or do we need to forget some information from previous step? So this step, what we'll do is whatever unnecessary information that we have in t minus 1, it will forget that particular information. Okay, so from here we will obtain st minus 1 point-wise multiplication with my forget gate. Okay, now just one small thing, we had at two places point-wise multiplication with st minus 1. Okay, both of these things sort of carries different meaning. Okay, so what I understand out of it is, over here when you are multiplying it point-wise with o of t minus 1, the output that you obtain, this ht minus 1, is sort of used in calculating this particular read quantity later on. Okay, so this sort of captures the information that you will use at the next step to calculate the intermediate representation for your xt. Okay, and when you are sort of calculating this s of t by forget gate, this is the information that you do not require further in your timeline. Okay, so these are sort of two different things. Okay, so this is the sort of complete structure of your LSTM. So in your RNN, what you had a very simple calculation. What you had is ST was nothing but this was W S of t minus 1 plus U of xt plus B, right? Now this ST has been modified a lot. Okay, Now what happens is, first of all, from your previous time step, you won't have st minus 1, you will have this st minus 1 dot ot minus 1, that is your ht minus 1, right? Then that ht minus 1 is used to calculate this st dot it. That thing is added to your st minus 1 dot f of t to obtain your s of t. So the way you calculated your s of t sort of has changed or have been modified in a better way in your LSTM. Okay. Now one more very small thing. Okay. So when we did this method, what approach did we follow? First of all, we did select write, right? Then we did select read. Then we did select remove or forget. Okay. Now this was good for understanding, but if you look at this coefficient, you have t minus 1 over here. So when you sort of implement an LSTM, the task till this point, like when you have to calculate h of t minus 1, is done in one iteration, and you begin your next sort of word. What you do is, you assume that you have this h of t minus 1 available with you. First of all, you perform your select read. Because you have h of t minus 1 available with you, you will perform the select read. Then you will go to select forget, right? After you have done your select forget, you will do a like point-wise multiplication and output the h of t. Okay, so this would be select right. So in sort of implementation wise, this is the path you're going to follow. So if somebody asks you what are the processes involved in LSTM, so you will start with select read, then you will go to select forget, then you will do select write, and this is the like flow that you're going to follow. Okay. Okay, any doubt in this LSTM thing before I move ahead? Okay, so there is a small one more small thing that we have, that is called GRU. Okay, GRU is just a variant of your GRU is just a variant of your LSTM, which has two modifications. First thing is, you have a this O of t that acts straight away on your S of t minus 1. Okay, so if you look at LSTM, O of t minus 1 used to act on this. Now you will learn this O of t in your current step that would act on S of t minus 1. This is one difference that you have. Okay, and till the output you will only leave till S of t. And the next step you will have, you will learn O of t plus 1 that will do this kind of computation. Okay, so now you have only two gates, that is your output and input gate. Okay, and your forget gate is sort of tied to your input gate. So if I of t is your input gate, you use 1 minus I of t as your forget gate. Okay, that's the only difference between GRU and your LSTM. Okay, everything remains same. So this structure is same, this structure is same, right? This thing is also same. So this is your h of t minus 1, w times h of t minus 1 plus u of xt plus b, right? And this thing is also, this is the only difference in this. Okay. Any doubt in GRU? Okay. Okay. This topic again, this is related to back propagation. I am not covering in lot of detail. Okay. So LSTM and GRU sort of takes care of this vanishing gradient problem and exploding gradient problem in a better way as compared to your RNNs. Now the reason is, I'll sort of try to motivate this thing. slightly, but I won't go into a lot of details. Okay, when you take yeah, I think yeah. These terms that you had, del S4 by del Sk, okay. So when you see this LSTM, when you are calculating S of t, right, your loss function of L of S of t would depend on these things, St plus It plus S of t minus 1 dot product with F of t, right. So when you take gradient of S of t with respect to S of t minus 1, rather than the usual channel that you have. So earlier you had this bound with respect to W and lambda something something that sort. Now you will have one more term because of this forget gate, because these two are just dot product, right, and that too point-wise dot product. So you will have an extra term of F of t on your bound. Okay, so this is what is the intuition why LSTM and GRUs perform slightly better in terms of this vanishing and exploding gradient problem. So when you have backward propagation, so the terms that you were multiplying that had very, so there were different terms that you were multiplying. If I can show you, these were the terms that you were multiplying and these were the terms that you bounded, right? Now these terms would be at least greater than or equal to, let's say, 0.5 if your gated GRU has values 0.5. Like that depends on the value of your sort of, again, your gated GRU. But let's say if it is 0.5, then it will be at least 0.5. So it will be 0.5 plus the bound that you had earlier. Okay. Now the thing is, if you have, let's say, 20 terms of 0.5 being multiplied by each other, then it is still small. Okay. But now the point that people make is, like, if you have 10 terms with gated GRU being multiplied by each other in the backward pass, then those terms would have been multiplied with each other in the forward pass too. Okay, because you would have 0.5 multiplied for the first forget pass, then 0.5, that term being multiplied by second 0.5 in the second forget pass, and so on, right? So because initial terms are making very negligible impact on the output of your further layers, so it is okay if they make negligible impact in modifying the loss for the further out. Okay, so in this way people say that because this your this what did I say? Yeah, forget gate control the flow of gradient. That's why you have a better performance in terms of vanishing gradient. Okay, so if there is a question, how does LSTM sort of takes care of your vanishing gradient problem? So you can say that because of this forget gate, it controls the flow of gradient. That's why we have a better performance. Okay. Okay. So I would request you to please answer these two questions. So these are similar to what we have discussed, or if you have any other doubts, you can ask. First of all, let's say sixth question. What do you think is the correct uh, like way to correct order to sort of do this thing? Somebody says C. Others also, can you please answer? So C is correct, right? This is what we just discussed, that first it will do read, then forget, and then write. Okay. And this last point we just discussed, that how does LSTM avoid vanishing gradient problem? So it uses forget gates to control the flow of gradients in backpropagation. Okay. So B is correct over here. Okay. Okay. Any doubts?